Hello, my name is David Saldaña, and today we are going to talk about how to do position control for mobile robots. In our problem, the robot is represented as a point that wants to move to a desired location. Our challenge is how to move from the initial location to the desired location. For that, we assume that we can control the robot velocity. The control input is denoted by U. To simplify the problem, we start studying a one-dimensional case. In this case, this is a train that is located on a track, and we know its position with respect to a reference. And then we want to move the robot to a desired location that in this case will be the station, or in other terms, it will be the location XD where we want to drive it. Then our control input is also the velocity, but in this case, this is a scalar value that will determine how fast the robot is moving on the track. I asked students about how to stop the train at this station, and I heard quite interesting answers. The first answer was about putting stroke magnets at the station. That is a very interesting solution, actually. The second one is about driving at constant speed, and once you reach the station, you just brake. We can write the control input for that. We drive at constant speed, and once we arrive at the station, we brake. If we plot time versus speed, we will figure out that there is a discontinuity, and that change will require a lot of energy and really good brakes. Today, we will study two approaches. One is open loop control, and the second one is closed loop control. Our first approach is the open loop control. We define a control policy that does not depend on the feedback at every time step. Then, this is very useful for fast actions for a short period of time. One example starts describing an error or a distance to the goal that we need to drive the robot. So in this case, we can just compute the error as the desired location minus the current location. And then we can create a control input that moves at constant velocity for certain amount of time. That amount of time can be computed just by dividing the distance that we want to travel over the velocity that we are traveling. Technically, that will take us to the station, so after that time passes, we can just stop and do anything else. This is a variation of the student's controller, and it seems like it will work. In theory, if we have a differential equation like this, when the velocity is our control input, that will work very well. However, these type of approaches, and not only the example there, but in general, most of the open loop control techniques, they don't take into account the disturbances. So if a disturbance comes and pushes the robot a little bit before or after. Disturbances can come from errors in the engines, in the actuators, errors in the wheels, disturbances from the environment such as wind that will make the robot reach different locations than the desired location. In our research with aerial robots, we have been using open loop control techniques for undocking. Imagine that you have two drones that are connected using magnets like the ones that we have in the pictures, and they need to separate. In this case, we used an open loop technique that creates this high torque towards the left and the other torque towards the right. And the combination of these two torques will make the robots break the magnetic connection so they can undock in midair. Introducing the measurements can lead us to have like a very accurate behavior, and we can correct the errors that we are having over time. So we don't have to wait until the end to realize that we didn't reach the position where we wanted to be. In this case, we take into account the measurements and we subtract them with the desired location. That is the error that we want to study here. Then we introduce our simple technique that is the position control. The position control takes into account the error, that is the difference between the desired and the current location, multiplies by a constant, a positive constant, and using this simple controller we can drive the robots toward the goal. The robot will always move in the direction of the desired location, and its speed will be proportional to the distance to the location. This is a really good technique. This works works very well in practice and also in the theory. And we will show that actually it works analytically in a different video. Then we can use the proportional controller to drive the robot towards a desired location. This is a two-dimensional problem, but this is a simple extension of the single-dimensional problem. The position controlling X and Y independently, we can see that we can drive both X and Y towards the desired coordinates. In this plot, we can see how the exponential function decays very quickly towards the desired location. We can actually put this method in practice and see how it works with an actual robot. If we have a robot that has an ultrasonic sensor or any distance sensor, we can come back to the single dimensional problem where we have a wall and we want to be at a specific distance from the wall. For example, we want to park at home. The sensor will give us the distance and we will set the desired distance. In this case, just for an example, let's say that we want to be at 50 centimeters from the wall. Then we can use the position control to drive the robot and actually stop when we reach the desired location. As a further reading, we have multiple properties that can be studied. The properties of the controller are stability and stability. We want to check if a controller is asymptotically stable or exponentially stable. I don't want to enter in details here, but you can go to the nonlinear system books by Professor Khalil and check that the P controller is actually exponentially stable in the settings that we describe in this session.